So we will now talk about the power flow problem and define it. So we can use those equations to actually solve them later in like Gauss-Seidel and Newton-Raphson methods. So here we can see the complex power SI that we have traditionally defined it like this. When we do the load flow problem developed to make it more easier to calculate, we actually do a complex conjugate of the SI. So we will get this value here. We get then Pi minus JQI equal VI complex conjugated current I. Multiply that. And then from generic outline I showed before, we can express the current as the product of the admittance times the voltage in every node. So this is a sum and the generic equation. We can also then have an expression for the VI like this. We can have VI equals the like traditional angles, or it can be expressed as VI, and then we have the cosine delta. Oh, let's see, that was wrong. Cosine for delta I minus J sinus delta I, like this. In the same way we can have for the admittance, in general form, see between I and J nodes, then we're using the angle theta for the admittance, or it can be expressed as Yj cosine to the pi j plus j sine theta I j, like this. So you can actually then insert the VI expression in here, and this, let's see, this admittance here in here, and then we can have total summation SI complex conjugate equals Pi minus JQI equal sum n equal I to n. If you look on this two-bus system up here, like total general, you can express it like this. Then we have the YIN, VI, and VN. So this is the overall equation for the load between node I. So you can see that what does this consist of? Remember that this VI is both a voltage length and angle, like you see here. The same for on the other side. So you can see from the load at node I, you have the admittance between node I and the respectively other node. Then we have the VI, VN, the voltage between them, and then of course we have the angles, and this is the theta for the admittance. Then we have a angle on the voltage on the one voltage side and the other. So this here is more like because it's not like an absolute angle, but more like a reference angle, we can say. Ref angle. And I saw also previous video that the angle difference, very much to say about the load flow. However, the the length of the voltage, not these voltages have much to say about the reactor power flow. So we can take now this equation and we can split them into an active and a reactive part. Let's take Pi first equals sum n equal 1 to n. Then we have cosine to angles plus minus delta I. There's an expression for the Pi, or the real value of SI complex you get. So if you have the SI, you can just simply MATLAB just plot the real value. And then for the Qi equals minus n equal 1 to n. The same. Now sine like this. And those equations, these are what we call the polar form. All the power flow equations. So those equations and they provide the calculated or transmitted values for the net real power. In another way, also can say that the imaginary value of SI. This you can find the reactor power flow. So just see that you have the admittance, the absolute value, the length of the vectors, and the voltage I, voltage of each of the buses, and then the angles between them, and also the angle to the admittance. So what are we actually calculating when we are trying to solve the problem? And one thing can be what we call the mismatch. Let's look at that. So if you have a generator connected to a bus I, and this generator delivers P 3I, Q 3I, typically. Then we have a load connected to that bus for PI demand and QDI demand. And then we can have other lines connected to that bus, for example. We can call them the PI, QI. And on that bus, if you look closer to this bus I, we can call it PI scheduled, actually, value entering. And we can also have what you call PI calculating, cal. So if we let's see, if we then write PI scheduled is P generator in minus P demand out, and this we can call the net scheduled power being being injected. So we can then define then a mismatch. We can call it then the delta pi on that node is the pi schedule minus pi calculated. And this means pi minus di minus pi calculated. And those mismatches then occur in the course of solving a power flow problem when you calculate on the PIQI and when it does not coincide with the schedule value. So as you can see, the schedule and the solution of the power flow. When you have this, so the solution and the schedule, and you have then a mismatch here. And then you can of course say, okay, I do another iteration, as you say, and then we can have until we have an okay mismatch in the system, or if you want to force it to 0. So we can come back to this. Another thing we are calculating is, of course, the real power loss, and we can, of course, let's call it PL, and that will be the sum. Oh, let's see, take it away again. The sum from all the nodes 1 to n pi equal the sum again n minus p di equal 1 to n. This is the total generation. This is the total load. So intuitively, of course, the difference between the total generated total load will give the real power losses, or what you call the I current R losses in lines. And also, of course, you can have one for the reactive power if that's of interest. In lines, and of course in some in transformers. Now let's talk about the classification of buses. That is also important. Let's go down here. So let's take classification of buses. And when you saw the power flow, there are then 4 unknowns that you typically say, and it is the PI, QI, VI, the length of the vector, and the angle, voltage angle. So P, Q, voltage level, and voltage angle is the typical variables you want to find in each iteration when you solve it. And we have 2 equations, and here we have 4 unknowns. So typically at every bus we have to specify 2 of them. The first bus we can classify. One, it's the load bus, or PQ bus. So in such a load bus, we typically know the demand of power, PDI, and QBI, the demand. Remember that this is typically used as negative sign drawn out of the bus. So here you specify typically these values for the load in your calculation. And often is PDE is as a demand of active power is given, and the Q need to be found about a cosinus function. Cosinus theta, or power. It's often given that the power factor PF is given to 0.9 inductive or something. It's typically specified on in that manner, and you need to find then the voltage level and the angle for the voltage. The second bus, we can take it over here. Number 2 is the voltage control PV buses. We can call it like a generator bus. Maybe that's easy to remember. Generator bus. So, and then it's written what we actually have specified. So the known, let's see, known here is then the is then of course the P E I, sorry, and the voltage. And you need to find the QI and the angle of the voltage. So in this we imagine that the voltage is kept constant. However, this is of course limited by the generator capacity, because remember that this one, that generator has a capability diagram with the P and Q. So if you need more, for example, reactive power, then you can actually access. Then you will have a warning, or you will not have a solution actually for the system if you make such a constraint on the calculation. Another thing is that you typically solve the load flow and you find the angles and everything, and then you need to find the after solving the power flow problem, you can calculate the reactive power from here. Also for the active power, we can of course have that demand of the prime mover, the active power of the turbine. So that can also be a limitation here. So that means that maybe if you can't get more active power, you need to transport it from another place, and then you will have losses in your system. That is something you have to think of, and you will then get, of course, a value for the mismatch and so on. The third is the, let's see, 3, it's the slack bus. Slack bus, someone call it infinity bus or swing bus. Another name. Or a reference bus is also. So every system you define in your calculation, you need to have a slack bus. That is typically a bus that are to the higher voltage level. Means like that the load can exchange through this bus what is necessary in your defined system. So in here we also do some define something, and one thing is that we typically define the voltage, and the angle of that bus. And one classic way is to put this as a 0 angle. Then this becomes like a reference value. And also very often we use this as a 1 per unit as a reference value. So, and then everything will swing according to that bus. And you find then how much active power and reactive power you need to draw or exchange to the other grid system. You should also note, I can say, that the VI, the angle voltage, the voltage angle and level are called then the state variables. Or dependent variables. So that means those describe the state of the system at any time. So if you have calculated the voltage length and the angle at every bus, you can, of course, this will lead to that you can find the currents that are flowing through the buses. So we are already talking about the power losses, but you can also have this the combined MVR reactive losses. You can have expression for those that also, like this: I1 to N QI equal the sum 1 to N minus to N demand. So generate demand, the same as for the active power. And this is actually it account for the combined VRs associated with line charging. What other shunt capacitors? Capacitors and reactors installed. The inductor component, the other is capacitive component. And then you calculate then the I squared x in the series of the transmission line. So this is also something you can calculate. So you typically then use like a equivalent as I learned before when you put it in your grid system. When you calculate, just take half of the each side when you calculate. And remember also that this is then you have to use the square root of 3 when you calculate those values, since it's per phase. So finally, let's just sum it up with this table as you have in your book. So as I said, the bus type, we have the slack or swing, you have the voltage controlled bus and the load bus. And here we have a table. You can have number of buses, what is specified, number of variable equations, and number of angle and voltage state variables need to find. So what is interesting here is that the slack, of course, that is just one bus that actually can be defined as a slack bus. Voltage controlled bus or PV buses. It has some NG, we can call it, numbers of generator buses. And then the load buses, we can find then the total minus generator buses minus ing bus will give us how many load buses we have. And the total of buses will be n. So this was the first column. The other column was the specified. So if you see on the voltage control bus, we have the active power and voltage length level, and then it's specified. So we need number of available equation, depends on then of course the how many buses we have, and also for the state variables. For the load buses, you can see here we have specified those values. And actually you can calculate now on the same way we did for the number of buses. Number of available equations will be 2. It's 2 equations per node. And then we will have, and the same, you will find the amount of equations. And the same on the state variables. So this gives an overview and summary of the power flow problem for before we start to do actually the calculations with the Gauss-Seidel and Newton-Raphson.